is Michael Gutperle. We'll talk about Spacelike branes.
Okay, can you hear me? Is it on? Yeah? Okay, I'd like to thank the organizers for the kind invitation to speak, and since I'm used to do what Mike Green tells me to do, I think I'm Robinson Bar. So this talk is based on some work I did with Andy Strominger and also a paper with Chianmai Chen, Galsop, and myself. And the basic premise and the basic idea, I mean, this work and I guess a lot of talks we will hear is to understand time-dependent backgrounds in string theory, and that is a challenge and also rewarding. So I mean, a couple of points of interest here is the question of the resolution of singularities in time-dependent backgrounds. Like we learned a lot about that in static backgrounds that, for example, strings don't really mind being on singular spaces like orbifolds. And so the question is, if I actually have a singularity which, for example, can be gotten by doing a time-dependent orbifold, whether strings will also resolve this. And obviously, I mean, the most important time-dependent background and maybe the biggest challenge for string theory is the application of string theory into cosmology. I mean, are there bouncing solutions? How to incorporate inflation, I mean, the cosmological constant, etc. Another point of view, I mean, another important idea is that in ADS-CFT we learned that there can be a holographic construction of a spacelike dimension, and I mean, an obvious question is whether there can also be something like a holographic construction of a time-like direction, and I mean, the de Sitter-CFT correspondence is maybe one idea to do this, but the question is this possible, and is this a really fruitful way to think about things? Then if you have time dependence, you in general have the possibility of the creation of particles or strings. So that is also an interesting area. And relatedly, I mean, questions of causality, locality, unitarity in time-dependent backgrounds, which have been kind of more understood in static backgrounds, also come up there. Another point of view was that in localized tachyon condensation, and I mean in general, it is actually believed that there is a connection between time evolution, on-shell time evolution, and renormalization group flow, in the sense that say renormalization group flow is irreversible, and say a condensation of the tachyon should correspond in an on-shell evolution to say energy being dissipated out, whereas in the renormalization group flow, say energy should be reduced. So it is believed that the endpoints of such dynamical evolution is the same. But the question is, I mean, is there a deeper connection? And then lastly, I mean, to really say something in string theory, we need exact backgrounds, and I mean, there are examples like these time-dependent orbifolds, or a Napi-Witten solution, or the rolling tachyons of Sen. So in this talk, I try to, I mean, present maybe some speculative work of trying to find a very simple realization of time dependence, and it's based on trying to generalize, I mean, and based on the importance of D-branes, what they have taught us in string theory. I mean, many things, and in particular to have sense construction of branes, lower dimensional branes, as tachyonic solitons in non-BPS or DD bar systems. And the question is, can we actually apply similar ideas to construct time-dependent solutions? And so a simple example is, say, in field theory, take a real scalar field which has a double well potential, and instead of trying to construct a spacelike kink, which would give us a lower dimensional time-like brane, we try to construct a kink in time. So, I mean, how this could work, one sets up initial conditions for this field that it is at the top of the potential and gives it a velocity so that it's about to roll down. Now, if this field is coupled to other fields, then it will roll down and eventually dissipate the energy into radiation and settle into this minimum. And so if I reverse this process in time, then what this means that you actually have finely tuned radiation coming in, where the field starts in the other minimum, and it actually will be pushed over the barrier. And then you have something like a time-like kink, which is localized in time, and in analogy with the standard sort of language, you would say that this is actually a brane which is space-like. So this, I mean, one can generalize these, this construction and construct solutions which are localized not just in the time dimension, but also in the space dimension. And this can be, I mean, for example, illustrated with a complex scalar field where you have a Mexican head potential, and then again you give initial condition such that at t equals 0, the field actually interpolates between two minima on the real line in z, and then you give it a velocity which actually turns on an imaginary part. And then what will happen is that the field will settle down into the vacuum manifold, but then if you, because of the imaginary part, it will actually go kind of clockwise, and if you reverse it, this means that radiation will push the field across, and in this zt plane, you will basically have something like that at large z and t, the field will describe a circle in the vacuum manifold. And to illustrate that you can actually couple this field, I mean, there is a U1 current associated with the phase of phi, and you can couple this field to an axion, and then on scales large to this thickness of this space-like brane, you would expect that this axion actually is sourced by a delta function, and so I can express the equations of motion like this, and that is solved in terms of a scalar function which basically satisfies the two-dimensional wave equation with a delta function source. And I can solve this, say, using the advanced and retarded Green's function, where the advanced and retarded Green's function are localized on the light cone and vanish in the future and the past. And so in some sense you can interpret this as being caused by the outgoing and incoming radiation. And in a sense, this solution carries a charge. I mean, where the charge is obviously a misnomer because the whole process is not time independent, but it is the analog quantity of, say, an axionic charge if I would actually construct a vortex, which would be the normal construction, say, for example, a la Sen. And so, I mean, an important comment is that such solutions will be invariant under Lorentz transformations in the transverse space, because the transverse space where the object will be localized contains time. And so, unlike in the standard case of time-like branes, you have a symmetry of rotations in the transverse space, which is associated, say, in the D-brane language with an asymmetry of the scalar fields, which give you the embedding of the branes. Here, the symmetry is actually a non-compact group of Lorentz transformations, and which, if one has a field theory realization of the degrees of freedom associated with a space-like brane, this would also correspond to an R-symmetry. So in string theory, one one can basically embed these field theory examples and use the construction of Sen, which constructed lower dimensional D-branes as kings or vortices of the tachyon field in brane-anti-brane systems or in non-BPSD brane systems. So, for example, the first construction of the time-like kink can in principle be embedded into string theory if you take the scalar field to be the real tachyon of a non-BPS p-brane, which has a coupling of the real tachyon to the Ramond-Ramond field. And so, in this sense, if I have a time-like kink of the tachyon field, then this solution will carry this, the integral over, will source this Ramond-Ramond field, and the appropriate integral will define a charge, which then sort of means that it is sensible to identify this space-like brane, which is localized in time, as an analog object than the usual time-like branes. So there's, there's actually maybe a realization, although the exact relation to this construction is not 100% clear, is the rolling tachyon solution of Sen, where he found an exact open string background where you neglect the coupling to closed strings. You work at zero string coupling, where you exactly start with a configuration where the expectation value of the tachyon is 0 and you give it a velocity. And then what actually happens there is that the tachyon approaches a constant velocity, so it will actually never reach the minimum, but it starts from one, with these initial conditions, it starts from one minimum and ends up in the other, and actually will have the integral over the source of the Ramond-Ramond field will be non-zero there. There's also, one can generalize these constructions further. For example, one example is to get a space-like object localized in a D3 brane, which is given by a configuration of the gauge fields on the D3 brane, which at late or early times actually comes from a settles down in vacua with different winding number sectors, and then such a configuration will actually be related to a sphaleron. An important point to make here, with the kinks and these branes or these configurations, that in no way they are really the analytic continuation of the well-known BPS instantons. For example, here, because we really work in real space, this is not such a configuration is not a self-dual configuration, because that would be a complex configuration. Here, we're really looking for real solutions. So in this sense, these time-like branes will not be BPS. So a separate way of approaching D-branes, which was very useful for the standard time-like branes, was also the boundary states. And one particular merit of the boundary states is that they make the coupling of the brane, as a topological defect and as defined as a defect where open strings can end, the coupling to the closed strings very manifest. And so, one way to construct a space-like brane is simply to look at the boundary state which satisfies Dirichlet boundary conditions in time. So, here I can define a boundary state which, say, depends on the spin structure, and the boundary conditions relate the left and the right movers, the bosonic and fermionic fields, via this matrix O, an orthogonal matrix. And here I demand that P plus 1 dimensions, actually space-like dimensions, satisfy Neumann boundary conditions, and the rest of the coordinates, including time, are localized and satisfy Dirichlet boundary conditions. And so this matrix then will impose these boundary conditions on the oscillators, and the complete boundary state would be a sum over the Neveu-Schwarz sector and the Ramond-Ramond sector with the appropriate choices of the spin structures. And so the coupling to the closed strings is easy to determine because the boundary state will act as a source for the on-shell closed string fields via this equation projected onto the on-shell states. And here we see, I mean, two things. One is that indeed, I mean, because there is a Ramond-Ramond part in the boundary state, this brane will act just as in the field theory example as a source for this Ramond-Ramond charge, and in the sense that the charge, I mean, will be exactly the same, I mean, basically by construction as the standard brane, but there are also quite significant differences. I mean, because the boundary state is localized in time, and I mean, this means basically on the zero modes, I have an integral over momenta, I mean, in the Dirichlet boundary conditions, and also the time component of the momentum, the energy. And so this is just the zero mode part of the boundary state, where I localize the state at time x0 and position x in the transverse space. But here this is quite different than the standard case, because this contains actually arbitrary values of k squared. So whereas in the standard case, you actually only integrate over space-like momenta. So this means that actually the source, the physical states in the standard open string, in the standard D-brane boundary state, will only be source physical states with zero momentum. And that is basically reflects the fact that the standard branes source the fields, the massless fields, just in a way of, I mean, associated with some kind of Coulomb interaction, which one can consistently incorporate via, I mean, from this source via Fischler-Susskind mechanism, and iteratively basically can get the supergravity solution, the supergravity fields associated with the brane. But here, because of the localization in time, we really have a source for not just the zero momentum massless field, but all the fields on the light cone, and furthermore, also even massive state, which are in the standard brane, I mean, in the standard boundary state, all unphysical are physical. So this seems to suggest that there will be a large back reaction, and so I mean, this is not so clear whether this simple boundary state is really a good description of a space-like brane, and how to, unlike in this case, how to consistently iterate this back reaction. I mean, this is still an open question, and related to that is the question of whether this asymmetry, which is manifest and exact in this boundary state, will actually get broken by the back reaction. And I mean, related, what in some sense is a thickness of a brane, which somehow should be related to the lifetime, say, of a brane-antibrane pair, and what is the energy. And I mean, actually in the past, these boundary states were also analyzed in different contexts. I mean, to, for example, look at the Hartz, incorporating Hartz scattering behavior in the string, or looking at an off-shell formulation of string theory. And in particular, Mike Green has looked at the analytic structure of these, of say, cylinder diagrams, which in the normal case would give you, I mean, would be one way to get the force. But here it's really a correlation, I mean, in the light, I mean, in these differences of the position, which has some, I mean, which has singularities on the light cone, again indicating that there will be a large back reaction. So these are 2 points of view, and I now will present a third point of view, is to try to look at the massless fields and find a supergravity solution which incorporates the features which we would like from such a space-like brane. And I mean, the features which we really want to incorporate are the symmetries. So in a normal brane solution, in a time-like brane solution, the world volume, which satisfies normal boundary conditions, has the time in it, and so the symmetry will be a Poincare symmetry of the world volume, and some rotational symmetry of the transverse space. For an space-like brane, we, on the other hand, would like to have just translation symmetry, translation and rotation symmetry, the Euclidean group of the world volume, because now this is a Euclidean world volume, and this symmetry, this asymmetry of the transverse directions, which now contains time and corresponds to Lorentz transformations. So again, in some sense, as in the case of the field theory, that these are not just the analytic, the continuations of the standard, say, instantons, for example. And there are different brane solutions which are called E-brane solutions in found by Hull, but these are not solutions of type 2 theory, but of in some sense, analytic continuation of type 2, which is called type 2 star theory, and these have quite different properties. So here, I give some more references. There was also a paper by Krushansky, Myers, and Pete analyzing supergravity solutions, and there's also been, some of them we became only aware after we did our work. Older work by Liu, Mukherjee, and Pope, and Lucas, Ovruth, and Waldrum, and Grosjean, Quevedo, Tassinato, and Zavala. So I go through maybe one simple example of the general idea, which is the four-dimensional Einstein-Maxwell theory. So I just have a gravitational field and a gauge field, and so I like to incorporate here, I will look at an S0 brane, which in maybe a bit of an abuse of notation will be a brane with a one-dimensional world volume. We still stick with the nomenclature, which is maybe even more perverse now in this context, that a p-brane has a p plus one-dimensional world volume. But so now in this case we have the symmetry of the light cone and the translation symmetry. So we take an ansatz like this, where this is the two-dimensional hyperbolic plane, and we also take a gauge field to be located, supported at the, this is the volume, the unit volume form on this hyperplane. So, one can simply plug in this ansatz and use Einstein's equations to find a solution. And what one finds here is quite a simple solution, where basically there are like harmonic functions appearing, and some of the interesting features here is that, in the t goes to infinity limit, I'll get a flat space, and so this the solutions become actually asymptotically flat, whereas at t0, where some of the components of the metric blow up, I'll actually have a horizon, and I can continue through this horizon, and I actually get a complete space-time with some time-like singularities here. So, in principle, this wedge should describe the region of the future light cone of this S0 brane. So that was maybe the simplest example. One can generalize this quite further. So we can take a supergravity action with a dilaton and some form field. And since I'm maybe not coming almost to the end again, we support a form field on the volume factor of this hyperbolic space, and I maybe don't bother you with too much of the details, but we can calculate we can get the equations of motion, and then the nice feature of this system, although it's quite complicated equations, by choosing a nice gauge, one can actually reduce all these equations to to two equations and decouple them for two scalar functions, and in this and simply solve them. I mean, here alpha and beta are just, and chi are just some constant depending on the parameters of the solutions. I mean, the dimensionality of the brane, the coupling constant of the Diller term to the form, etc. So, I mean, here we have the solutions. And again, in the limit, I mean, although I use different coordinates here, t going to t1 corresponds actually to going to infinity. Again, the metric becomes asymptotically flat. But here, in general, for generic values of the coupling constants, I will actually have a singularity at t goes to infinity, which actually in this parameterization corresponds to the near brane region. I mean, the Ricci actually is constant, but higher curvature invariants blow up. So these solutions can be generalized. I mean, one can take not just hyperbolic sections, but flat or spherical sections. And then actually, in this case, very often these actually are related to known solution by analytic continuation, in particular the black branes solutions. So I want just one more thing to say, that a non-isotropic solution where I break the Poincare symmetry will actually be non-singular and looks very much like the S0 brane. I mean, that was pointed out by Grosjean and so my time is up, and I want to conclude. And so I say that time dependence in string theory is definitely a timely problem. I mean, I think it's very rewarding to think about this, and I hope I have given some indication that these space-like branes might prove useful as an idea for a simple realization of time dependence in string theory. And we advocated three different points of view: time-like kinks, tachyonic solitons, the boundary state, and the supergravity solutions. And it's still not clear how actually all these three different descriptions tie all together, and whether they actually all describe the same. Thank you very much.
Questions? Andy.
I'd just like to make a comment that I think that Sen's construction of space-like branes is... Can you hear? Can you hear? Is it on? Okay, I'd just like to comment that I think Sen's construction of the space-like branes as was an improvement over the conformal field theory that Michael and I presented, in that it was closer both to the original picture as a tachyon soliton, furthermore was free of the large back reaction problem that we had in trying to describe things as the Dirichlet brane picture may be an approximation, which we still understand. The Finch-Gordon model looks like a very precise description of the whole story.
Well, in the supergravity description of the ordinary branes, one often has a singularity at the location of the brane. Now, it wasn't clear to me in the supergravity solutions you described, there were some time-like singularities. Is that where the brane is supposed to be, or is the brane actually the center point, which is non-singular?
Well, I mean, I guess, I mean, these solutions actually, I mean, look in some sense like two universes connected by a throat. So, but then, I mean, so it's not 100% clear, I mean, whether these solutions, I mean, where the brane actually is, because you would have you actually have a time-like singularity in, I mean, in the other wedges.
But in terms of the symmetries, it looked like the brane should be sitting at that non-singular point.
That's right. So, but then, I mean, then it's not, I mean, okay, then it's not so clear whether there would be a source there.
I would like to make a comment. Okay. My comment is like this. I like to make a comment, and my comment is like this. When you want to extend quantum mechanics to analytic variables, you find something very interesting happening. It is nothing but a unification of Feynman and Wiener path integrals. And the Planck's constant h gets replaced by a constant whose dimensions is that of energy. And such extensions are naturally found to have what are called the so-called charges. Internal electron and other charges are present there in them. And much more importantly, assuming, I mean, this is the crucial point, here the conformal symmetry is completely broken, contrary to string theory, and the thing that happens is the theory becomes the so-called Fourier symmetry is eliminated, and you get the mass spectrum of particles by assuming electron to be nothing but a mass-defining parameter. Mass spectrum of the particles that really exist by assuming the electron. Some of these results I have published.
Okay, let's thank the speaker again.